Okay, so where the last video ended, if you remember, I had attached my pen to the box, and the box was oscillating back and forth, and I was going to move the paper behind the box. So, like, imagine that the box is against a wall, and then the paper is being scrolled upward as the box oscillates back and forth. So if the paper is being scrolled upward, the pen's going to make a design on the paper that looks like this. And if you draw a dotted line down through the center and turn your head sideways, you'll see this is a sine wave. It's a sine wave that has an amplitude right here. And so earlier when I said I had pulled the box out some distance A, that wasn't an accident that I picked A. A stands for amplitude. So whenever they say in a question that it has an amplitude of, they're really telling you the maximum stretch or the maximum compression of the spring. Okay? Now, obviously, how quickly this thing is vibrating. This is a wave, and in a wave, remember, period is important. Oh, sorry. So that's where the word sinusoidal comes from, because it's a sine wave. So the other part of a wave is its period, its frequency, how quickly it goes through a full cycle in a given period of time. So period, we know, is simply a time. It's the amount of time for one full cycle. So if I stood here with my stopwatch, and a full cycle is all the way over and back out to where it started. So if I stood here with my stopwatch, and I counted 20 cycles, and I found it was 40 seconds, then my period would be 40 seconds over 20, or 20 seconds. Remember, frequency, as a little aside, we don't really use frequency in this unit, but frequency is 1 over period, or frequency is the number of cycles over a given period of time. And we use that a lot in the wave unit in grade 11 physics, but it's more the period we're thinking about now. And the reason we're thinking about the period and going to use it is because the period of this simple harmonic oscillator is dependent on two characteristics of the system. One is the mass of the box. How big the box is going to depend on how quickly it's going to vibrate. And the other is the spring constant, the K of the spring. Because how thick or heavy duty the spring is going to change how quickly it vibrates compared to if it was a wimpy little pin, a click pin spring. So the K and the M are both going to come into play in the period. And so we can use the period to find the spring constant. But I jump ahead. First, so we're going to use, with these questions, our conservation of energy equation. So 1/2 mg initial squared, mgh initial, 1/2 kx initial squared is equal to 1/2 mv final squared, mgh final, 1/2 kx final squared plus E lost. And always for simple harmonic oscillators, there'll be no E lost. Okay? And if you think about your MGH, it's on a level surface, so it's always that surface is always going to be frictionless, so no E lost. But it's also always going to be level, which means whatever its initial height was, its final height will be the same, so we can call it 0. So what you're going to end up with is the kinetic energy and the elastic potential energy on either side. I tend to call this side the initial, where I pulled it out. But it really doesn't matter. So if I did that, then out there it doesn't have a speed, but it has an x, so it's all elastic potential energy. And then in the middle, it has a speed, but its x is 0, so in the middle it's all kinetic energy. And most times, 80% of the questions will be dealing with these two places. There'll be a few of them that will ask you, well, what's the speed some distance from the rest position where it won't be the amplitude? And in that case, then in the final, you'd have both kinetic and elastic potential energy. And you'd know either the x or the v, and you'd be solving for the other. Okay, so this is one equation that we use for these questions. I already said this was one equation. And then the third one is an equation that's connecting t with the k. And it's t equals 2 pi root m over k. Remember a few minutes ago I said how heavy duty the spring is, the K, and how big the mass is on the end is going to affect how quickly it goes back and forth. Now the 2 pi comes from the fact that it's sinusoidal, it's a sine wave, and it's a unit circle. So if you think of a unit circle, right, the circumference is 2 pi r. So if we go back to our grade 10 equation, V is equal to delta D over delta T, the D is 2 pi r, and the T is the period. All right, and so if I'm just deriving this here, you don't need to worry about it. But if I were to say, all right, so let's find the speed when I pulled it all the way out to the end, when x is k, when x is a. So when x initial equals a, then we will end, and we're using the center point, so we would have 1/2 mv initial squared plus 1/2, I'm just rewriting up here the things I had crossed out earlier, squared will be equal to 1/2 mv final squared plus 1/2 kx final squared. So when x is a, this is 0, and if we're talking about the max speed, the x is 0, so we're picking the middle spot there. So we'll have 1/2 mv squared is equal to 1/2 k a squared, because I said x was a. Oh, and I think I switched the sides. Sorry about that. It doesn't really matter. Half and half, so here I made this final instead of initial. Halves go, and if I rearrange this, then for a squared, I would have mv squared over k. So a squared is a is equal to the square root of m over k, and then this would just be v. But v is 2 pi r over t. So a is equal to the square root m over k times 2 pi r over t. Okay? Or so I want t. So I bring my t up. And remember, r was a. So I bring my t up, I bring my a down. I have square root m over k. And this is 2 pi a over a. And the a's cancel. So I end up with 2 pi root m over k, which is the equation that I showed you up top. Okay, so just so you know, I didn't make it up. So 3 equations: t equals delta t over n, t equals 2 pi root m over k, and our conservation one. What will happen a lot of times is you'll use this one to find the t, and then use this one to get the k to go here. So your homework, or your suggested questions, page 608, yeah, I jumped ahead in the textbook, numbers 1 to 4. Give these a shot.